All right. Welcome to another PMSA member seminar. It is a pleasure to have Professor Konstantin Khanin, who is going to talk about another look at the KPZ problem.
Thank you very much. It's a very challenging task because I decided to do Blackboard talk despite certain resistance among some of the organizers. So you have to stay with me to prove that it's possible. And so I call it another look at KPZ problem, but you have first to say which KPZ problem, because there are two KPZ problems. And unfortunately, both of them can be at the same meeting, but they're completely different ways, although they both are related to random geometry. So it's Kardar-Parisi-Zhang problem. And it was mentioned already at least once. I was present when it was a talk of Professor Funaki, and he was mentioning it several times. I must say that despite the name of Parisi there, he was probably not the main actor, the main character of this paper of three. Probably Kardar was the main one. And I would say this paper is not a Nobel Prize winner paper. I mean, it's a pretty simple paper. And the whole phenomena was discovered much later, and mostly by a mathematician. And so my talk will be not about the equation, KPZ equation, which was written by Professor Funaki. And I should not go here. See? So it's HT plus nabla H square equal to nu Laplacian H plus white noise, space-time white noise. So that's what is called KPZ equation, and intricacies of its behavior on the small distances is a part of the Fields medal and deserved Fields medal of Martin Heirer. But the talk is not about that, because what we'll discuss will happen not on the small distances, but on the large distances and the large times. And what I want people to kind of get out of this talk is that this description of this phenomena, and this is phenomena. And many problems remain open mathematically, although we strongly believe that answers are and predictions are correct. But that is still open, despite many efforts in the last 15 or more years and spectacular results. A lot of this problem is still open, and I want to describe the phenomena. So phenomena is an extreme generality, and it happens on two-dimensional plane. So two-dimension is crucial. If you go to one dimension, nothing happened, and high dimension, nobody knows what happened. So you have a two-dimensional plane, that would be my plane, and you have some profile, what I call it landscape, of hills and valleys. And say it again? At? Euclidean. No, I mean, it's so it's like you live on a plane and then you have mountains and valleys and whatever. And what I want to do is to see what will be the behavior of, so it's a random profile, order one. So we are going in a very large distance. So the height of these mountains and the height and the deepness of the valleys is bounded, basically, order one. And we're going on a very large distance. And we want to take two faraway points and connect them by geodesic. And so we take points A and B, and distance between them is huge. So distance between them, Euclidean distance, we kind of project them on a plane, but the height is order one, so it doesn't matter. And the length will be L, and it will be much greater than one, and will go to infinity. Not one, but L will go to infinity. And then you want to find what will be the geodesic. You want to probably avoid very high peaks, and you want to avoid very deep valleys. So you want to find geodesic connecting these 2 points. And 2 objects of interest are, what is the length of this geodesic? And what is the shape of this geodesic? And basically say, since I fixed 2 endpoints, how far it deviates from the straight line, which will be Euclidean one. So 2 questions. The length of this geodesic, which depends on A and B, and which is a random variable because the profile is random. And we want to understand statistics of this thing. And we want to see, say, transversal fluctuations. How far you go, deviate from the straight line, say, in the middle of this path, or something like that. Now, this thing, of course, will go to infinity when L goes to infinity. And will be proportional to L. This is not an interesting question. So what is, people understand quite well that if you take LAB and divided by L, it converges almost surely to some number. And this number is not universal, is not of great interest. But it's a random variable, it has probability distribution. So what you normally do, you just subtract the mean value, which will be L times L. And then you want to see how big are fluctuations of the thing. So if you subtract the mean value of it. And it turns out the fluctuations will be of order L to the 1/3. And moreover, if you divide this probability distribution L to 1, normalize it, I put some number alpha, but let's avoid it. And then take limit in distribution, the probability distribution when L goes to infinity, you'll get universal law here. And it will not depend on details how distributed your hills and valleys. Doesn't matter how they distributed. If they're independent on large distances, you have the same law here. And this law is something that's called Tracy-Widom law, which appears in a setting of random matrices. And there are several Tracy-Widom laws. In this particular case, when you fix 2 endpoints, it will be GUE, Gaussian unitary ensemble Tracy-Widom law. This is particular one-dimensional probability distribution, universal. So the key word, which I'm going to explain today, is universality. And that's very important. And this will be less important for me, but it's important here, integrability. So universality means that the limiting law is one. It doesn't depend on details of your probability distribution, of your noise, of your randomness, of your disorder. And that's universality. And integrability is that you can say, in many cases, you can say what the limit law will be. Now, this is a density, which I cannot write formula for this density, like for Gaussian law. But I can say, people know everything about this density. So this will be density of this Tracy-Widom law. It will be certain density, which will be asymmetric. It will decay on one tail and another tail differently. And one decay will be e to the minus x cubed, and another will be e to the minus x to the 3/2, but doesn't matter. It's particular curve, particular density, limiting density, like Gaussian. And it appears all the time. You change setting, the many settings you can, for expert, I can say that when I consider geodesic, it means in terms of statistical mechanics, it would correspond to 0 temperature regime. But you consider positive temperature when you consider all paths connecting the thing and weight them with proportional to their length, and you will have the same limiting behavior. So it's very unusual situation where limits are universal. Integrability, you can say something about them. And my task is to understand why it is universal. Say it again. Well, it's a very good question. So there is a bench of models, a zoo of models with particular disorder, where the miracle happens and you can calculate things. And when you calculate, you get the answers. But what you say that if you change this particular zoo for something else, then nothing is known, basically. Right? Although we strongly believe that that will be the limit. Now, this guy also would have universal behavior. And if I have this delta, it will scale. So the mean value of it will be 0. I don't need to subtract anything. I mean, it's sometimes positive, sometimes negative. But if I divide it by L to the 2/3, that would be normalization. Not 1/3, but 2/3. That would converge also to universal law, which doesn't have name, actually. But it will be universal. So everything is this problem universal, and there is actually much more things you can say about it. But that's phenomena. That if you are in two-dimensional disordered plane and you want to go on the large distances and measure distances or lengths or something like that, then you will see this behavior. Now, I didn't write formula for the distribution for the metric. I didn't write formula how to calculate the length. So instead, I would do the following. I'll go to completely precise setting where this problem can be formulated on a lattice. You know, on a lattice, it's easier to live, and things will be very clear. So my lattice will be Z2, two-dimensional lattice. 2 dimensions is essential. And I would think that I have time direction, this will be direction from A to B, and transversal direction from A to B. So for transversal will be kind of space, and going down will be time. And then what means disorder? That at every point of this two-dimensional lattice, so if you have a point I, which belongs to, well, let it be x, I will be point, x will be space, and I time belonging to this two-dimensional lattice, there is a random variable attached to it. At every point, there is a random variable. And the field of this random variables for all points is IID, what is called identically distributed independent random variables. So that's my disorder. And now what you want to do, you go from certain points, say from the origin, this is my x, and time will go in this direction. And I go and consider random walk on this lattice. Actually, doesn't matter, but it's always good to consider random walk which doesn't go plus or minus, but also can stay at a point. It's called lazy random walk, but it doesn't matter. So you consider all random walks of length n. So the time, final time is n. And for this particular random walk, you can calculate its action. Action is like a length of it. So it is sum of this random variable along the curve. So it's like some dust, and you want to get as little dust as possible. And you want to find minimizing curve, which of course will be random. It depends on the realization of these random variables, which is what I would say argmin of this quantity for all gamma. So on which path this minimum will realize? What is the path of minimal action? And then the problem which I formulated here, now this I changed slightly problem. The endpoint here is fixed, and here is what is called from point to a line. I'm not fixing I can, for example, ask it to come to the same point, but maybe just going to any point on the line. Similar problem. And so if I consider the action of this minimizing path and subtract constant time n, which is non-random constant, which is not interested, and normalize it on n to the 1/3, that would converge to Tracy-Widom law. And this manifestation of the same phenomena. It's exactly the same problem, but just on the lattice, you don't have any problems. It's well-defined. And this Tracy-Widom law will be Gaussian orthogonal ensemble, because we're going not from point to point, but from point to line, but it's very well understood how to go from one to another. And if I consider fluctuation, here I can take just distance between starting point and the end point, then delta divided by n to the 1/2 also converts to universal law. So that's phenomena. All right. Now, what Kardar-Parisi-Zhang did, they said that it will be n to the 1/3 and n to the 2/3. Just scalings. They didn't say anything about limiting law. They didn't know it's universal. I mean, they didn't care about it, actually. It was discovered much later. And now I said it was a lot of effort. So basically, there are two objects here. The statistics of the action or length and the geometry of this path, how it will find its position. And most of the efforts were concentrated on statistics of these actions. And people, I cannot even name everybody, but many players worked on this, Kurt Johansson, Akunkov, Borodin, Jeremy Quastel, Ivan Korvin. I mean, a lot of people worked it, and by now a lot is known for particular models, but it's believed to be universal. And what I'm mostly interested, not what is the exact form of the probability distribution of this law, but why it's universal. And that's what I want to discuss with you. Is it clear what I'm saying? I think it's very simple. This phenomena, we have to, it's a real phenomena. It's not invented by us. It's just nature have this phenomenon. Yes? To? Yes, it is related to SF. So there are many exact solutions coming from the interactive particle systems, which are equivalent to these models. It's correct. Say it again? Yes, universality is everywhere. I mean, all the things are universal. All right. So let me just going from this. So as I said, there are much more we can say. For example, you can start from different points and consider minimizers starting from different points and then record their actions. And then when you rescale X, you get a process which is called Airy process, which is also universal. So the correlations are universal. Everything is universal. I'm not going into it. I want to have another look at the problem where I just look on geometry of the path and nothing more. And allow me just to kind of switch from discrete setting to continuous setting because it doesn't matter. It's actually the same phenomenon. So what I want to look at, I want to start from many points at time 0. And then I want to consider this path going infinitely long. Actually, you can prove that there are infinitely long paths going optimal paths, which what it means is that you can see the path going from here to the line and then n goes to infinity. It turns out that the path will stabilize. So you will have infinitely long path. Or if you physicist, you can think that you have very, very long path, and then you would record it on a long but much shorter interval of time. Anyway, so what I want to see that this infinitely long path, how it will look if I look at a time n, and the path is very long, how they would look starting from different points of the thing. And there is a general principle that when you have random dynamics, random transport from here to there, which consists of time 1, 2, and so on, time n, when you iterate random monotone maps, and it's essential to say that these minimizers cannot cross each other. If one was to the right, it will remain to the right. That's a property of minimizing, that they're not crossing. So the map which maps from here to here is monotone map. And when you iterate monotone maps, what will happen that most points will come very close together. But some will be split, separated. And that's an avoidable phenomenon. So what you will see that there is a whole interval of points which ended up in a very small interval. On the lattice, it will be just one point. So they start here, maybe they go separate way, but then they coalesce together and they come to this place. And then it would have another interval, and they would end up in another place. So when you take limit, when n goes to infinity, the map from here to here would be monotone, because everything is monotone. And it will be piecewise constant. Because the whole interval ends up at one point, and then another interval ends up at one. So where are scalings? The scalings are here. This length of this interval, although it's random, it will be n to the 2/3 order. And the length here will be also order n to the 2/3. So if you want to get something order 1, you just rescale time, the time space by n to the 2/3, and you get map. And so this time n, but we would think it's time 1, and you get time 1 map from 0 to rescale time 1, which take rescale point y and transform it to another point here. And this will be monotone piecewise constant map. So how such maps look like? What is the graph of this map? Well, they look the following way. So this is y, and this is its image. So you take diagonal. You cannot deviate too much from the diagonal. And it's just something random going along the diagonal. That's a graph of your map. Inverse map is also piecewise constant and monotone. All right. And now let's think that we have a sequence of this map. So one from time 0 to 1, and then from time 1 to time 2, rescale time 2 to 2n. Here's time 1, rescale time. Time 2, rescale time. Now, but there are very few points here. But now I start infinitely long paths from every point of this line. And then I get normal map going from here to there. And then from 2 to 3 and so on. And because of stationarity, this will be, because it doesn't matter. I start from here, they're infinitely long. It will be the same distribution of this map. So what I'll get sequence of maps. And these maps will be monotone. This is very important. Piecewise constant, less important, but they will be piecewise constant. And this is a stationary sequence of maps, of monotone maps. Infinite sequence. They're correlated. Although disorder here and there is not correlated, independent, but they're correlated because they're coming from infinitely long paths. So they know that they will be using the same space here, the same disorder here. So they're correlated. And then because of their correlation, the scaling n to the third, not square root of n, right? And and that may be another message which I want to say, that whenever physicists realize it in 60s, mathematicians, it took longer time, maybe in statistical mechanics in 70s, in dynamical system, end of 70s, 80s. Whenever you have some universal numbers, you have to look for renormalization group, renormalization transformation. And there are some fixed points of this renormalization transformation. And that is always the case, and this is extremely powerful ideology. Unfortunately, it's very difficult to prove usually. So much so that just to prove this type of statement for Ising model or Ising model, it's a Fields medal. But the ideology is extremely general, and it's kind of, it's very powerful ideology, good to understand. So here we have these universal numbers and universal laws. So there is some kind of fixed point. And I want to define the renormalization transformation, which will be acting on space of stationary sequences of monotone maps. So I start with one sequence, and I produce another sequence. I produce another sequence starting from that one. And the renormalization transformation takes one sequence, stationary sequence, so probability distribution of this sequence to that probability distribution. So what you do, you just combine them together and iterate them in pairs. So you go from time 1, rescale time 2. But you also, so you take, you're going from 0 to 1 and then from 1 to 2. But you also have to rescale x, because previous scaling will correspond to time n, now we have time 2n. So that would be your new sequence. You can ask me what is the number alpha? Well, just fix some normalization condition. So think that here the displacement by this map of say any point is the same, say over the origin has variance 1. And so choose alpha so that for this thing also variance will be 1. Then it's well defined. So this is the renormalization transformation, which acts in the space of this thing. And obviously, from construction, it's clear that we converge, the limiting procedure would converge to fixed point of this, that what the limiting sequence of maps would have the property that when we apply the transformation, you get exactly the same sequence of maps in the law. Say it again? Well, one would hope to have it, it's correct, yes. And then the question is, where is 2/3 here? There is no 2/3 here. You can consider anything. I mean, for example, what is 2/3? It means that if I iterate this thing n times, and apply to any point, then this distance will be order n to the alpha, and can be any alpha, too many alphas, n to the beta. So beta happens to be 2/3 for this particular problem. But in principle, you can consider any beta. So it's a question of describing fixed point for this transformation in the class of monotone maps. And the conjecture which I kind of put forward is that, in fact, for any beta, there is one fixed point which is stable apart from this neutral direction, the direction of parameter beta. So if beta is fixed, then under this transformation, you will converge to fixed point. And it will be just universal law. So basically, the condition of you live in one-dimensional space. And to live in one-dimensional space, you really don't have much room. You kind of have neighbors from everywhere. It's very annoying. And you have to adjust yourself and adjust the whole situation. But basically I would say that it's extremely rigid. So the only way to adjust it if beta is known to you is just one statistics. There is no others. So that's conjecture. It put this problem of universality for KPZ into a more general setting of a parameter beta. Here beta is any parameter, and I would put it between 1 and 1/2 to be on the safe side. But in principle, it can be from 0 to 1. All right. Now, we can put any conjecture you want, but you have to have some reasons that this conjecture might be correct. So there are two cases which we understand to a certain extent. So we think that, first of all, KPZ universality is a fact which we observe experimentally. But there are particular values of beta which are simple. And one value of beta which is very simple, it's 1/2. So it's what is called diffusive scaling. The point after you iterate it 10 times goes a distance of the square root of n from its initial position. So this beta corresponds to situation when these maps, this sequence of maps, they're independent maps. This is ID. So if you do independent maps every time, choose them independently, identically distributed, then you can show that you will converge to concrete distribution, to concrete map. And you can describe this fixed point. And moreover, you can prove that you converge with a power law which corresponds to stability of this point. Now I want to describe this fixed point. So where you will converge. There is no surprise here because it's a simple situation. So to construct it, you do the following. You consider a process which is called coalescent Brownian motion. This process was known from end of 70s. It was constructed by Richard Aratia at the end of 70s. So what the game you're playing is the following. You start from a real line. I'm sorry, my time now go up. And on a real line, you start from every point, and you start with independent Brownian motion. You can think it's not Brownian motion, but random walk. So at every point is independent random walk. And then the game is the following. When they two random walks meet, they glue together and continue as a one random walk. And Richard Aratia proved that although you start from continuum of points, which creates certain difficulties, after any positive time, you'll have only a discrete set of points which are reached. All the rest will coalesce already between them. So if you take time 1, what you will see is just point field, random point field of points which are reached, and the other points are not reached. So that's where only in one of those points these Brownian motions will end up. All others will glue together. And of course, because there is monotonicity, if they meet, they glue together, you have here interval of points which are coming here everywhere, which started in this interval would end up at this point, and then everything which started in this interval would come to this point, and so on. So you get the same type of map, piecewise monotone, piecewise constant monotone map, but say this will be time 1. I'm not taking in any limiting process. So it's time one map for coalescent Brownian motions. And because Brownian motions are scaling invariant, it's pretty clear that what you said time 2 will be the same up to the scaling. So it's obvious that this time 1 map is a fixed point for the thing. So if you start with a sequence which are time 1 map for coalescent Brownian motions and apply this transformation now, you will get exactly the same thing with the scaling being square root of 2. Alpha will be square root of 2. And what we can prove, is Li and Li, who now is Shenzhen Tech, that the rate of convergence here is exponential, is power law in n. So if you start with anything else, not from time 1 map, but with independent maps, and apply the transformation, and after n, after n application of this transformation, what you get will be close to a fixed point. So you take some other sequence, you apply Rn, and this is close to fixed point, and the distance will be of the order of some constant in power minus power n, gamma between 0 and 1. So exponentially, exponentially close to the fixed point. But of course, it is a doubling transformation. So this, if you take m steps, it means 2 to the n steps of iteration. So it's power law in terms of n. Doesn't matter. Now, what we don't know, and which we do numerically, we consider what is called coalescent fractional Brownian motion. Now, this is for brave people. Fractional Brownian motion, nobody probably don't like it. But actually, it's very similar thing for Brownian motions. It's also very wiggly. The only thing is that it's not Markovian process. What you do in the future depends on what you did in the past. And it's like you have Brownian motion, random walk, but if it's Brownian motion, your random walk every time go with probability 1/2 to the right, 1/2 to the left. And here you kind of sample what you did in the past and do the same what you did in the past. That will be fractional Brownian motion. And fractional Brownian motions deviate not on square root of n, but on an n distance parameter h, which is called Hertz exponent. And normally Hertz exponent is between 1 and 0, not always. And 1/2 corresponds to normal Brownian motion. It's positively correlated between 1/2 and 1, and negatively between 0 and 1/2. That's why I want between 1/2 and 1. And we consider a particular value of h equal to 2/3 because we want to mimic this problem, which we started from. And then we looked at this transport map and properties, statistical properties of this transport map in this situation, and for this case, which I described there. And numerically, we see that they're very similar. Numerically, you cannot say they're the same, but they're very similar. So there is good chance that this is the same fixed point, and they're the same distribution. And nobody would say that this problem is supposed to be in the universality class of KPZ. It is not. But what our philosophy is that actually rigidity is coming from monotonicity and prescribe displacement giving my parameter beta. So that's a set of problems, and answer not known. But then you can ask me, that's about geometry. What about the actions? How do you recover Tracy Widom or something? I would not recover the Tracy Widom at all. But what I want to say that suppose now I was taking time 0, 1, 1, 2, and so on. There is no need to do it. You can take any time, any rescale time s. So you have a floor. And you just rescale this time and you get a fixed point. And suppose you know the statistic for all s. And then you ask, how many distributions of action are consistent with the given geometry, with the given statistic of geometry? And I believe it's just only one. If this either 0 or 1, I'm not sure that all of them can be described as minimization problem. But if minimization problem describe the same statistics, then it should be the same prescribed distribution of the actions. But that's another problem. So the problem of universality, the roadmap is the following. You first want to understand whether this is correct or not. Even numerically would be a big thing because it will just tell you that what is essential and what is not essential. And then you want to understand connection with a thing like Airy processes and Tracy Widom, but that's a long story. And I'm afraid that you will be unhappy, and you. So let me just stop here. Yes. But can he ask question?
Let's first thank him.
Phenomena you describe. So how it connected with the equation?
How
all the phenomena is connected with your first equation which you have?
It's a good question. It will take a little bit more time, but maybe I can give you a little bit so equation which was described by KPZ. It's an interface growing equation. It's an equation which is describe growing interface between kind of two phases. In the easiest variant is the following: you have you put some bricks in random positions, and these bricks have a property that if you put one nearby another, they glue together. I mean, one goes on top of the other. So it's like you have bricks. So you have infinite line. Your physicist, so from 0 to L, and L will be very, very large. And brick is size 1. You put brick here, and that has a little wing. If you next time you put it there, it would go here, not going down, because it's stuck there. And then you play this game, you put more and more bricks. And then you'll get certain interface between here there is nothing, and here there are maybe some holes, but there are bricks here. And then you can show that this problem is described as minimization problem. And it's also described in this equation. So that's one of the explanations how interface is connected to this.
More questions?
I have a sort of a naive geometric question. So in that figure on your right side, the path from the lower line, I think that was time equal to 0 for you, and the upper line was time equal to 1 or something like that. So what happens at the endpoints? You said that a certain interval will, the smallest path or the minimum path will sort of converge to one point, right? And then the next adjacent interval will converge to a different point. So my question is, what happens at the endpoints?
Yeah, it's again good question. The previous speaker was praising people who are asking questions. I have to do the same. So in principle, if you are in not discrete situation but continuous situation, and for a large time but fixed time, what you will see is that there is not one point. There is an exponentially small in time interval which extends to long interval here. Right? So it extends. But when you're in a kind of in a singular situation, then it becomes a point. But in principle, in continuous case, if you have smooth case and smooth forcing and stuff like that, so the good, by the way, it's a good point to say that this forcing white noise in X and time, white in T is not a problem. The problem for Martin Harrer was white in X. That's what creates problem. But I can formulate formula when you have random forcing, which is not white but has correlation length in X, and then trajectories will be smooth in X, and then situation will be like that. It will be certain exponentially small interval. So there's exponential instability. So a lot of things get together, but little random pieces get very long. But the positions is random. It is prescribed by the distribution of disorder.
Just sort of follow-up question. Do you is there something related to a fractal that's happening here? Because some points you take an iterative process, it will blow up. At some points it will converge. It sort of feels
I don't see
like
fractal here.
Okay.
You have to explain it to me. But I mean, I like fractals, but I don't see fractals here.
Okay. Thank you.
Although, yes, Brownian motion is a fractal object, and fractal Brownian motion is also a Brownian fractal object, but that's the only connection.
Just since you mentioned this,
Is it on?
Since you mentioned the connection to these falling bricks, so I just wanted to say that those have also been studied from a different perspective by Vershik and Nechayev, with these statistical properties of braid groups can be seen as generators of braid groups. And I don't know how much that connection is.
Well, the paper with about bricks, which were written in a physical paper, it is with Nechayev as well. So there is a connection.
More questions?
Is there a relativistic version? Relativistic version.
Relativistic version. Okay. So why don't you ask about quantum version?
That's the next question.
That's the next question. For students, I mean, there is advice. I mean, if you have to ask a question and you don't know what to ask, you ask, what about multidimensional generalizations? Always works. If it's multidimensional situation, then you ask about infinite dimensional generalizations. That not always works, but you will not look.
I mean, you don't have to have del T plus P squared.
I don't know anything about relativistic version of it. Really don't know anything. I mean, we have enough hard time with this problem than to go to relativistic yet. We don't understand the basic things here yet.
So can I ask you some naive questions.
Yes.
In this, I was thinking about if we induce inhomogeneity in the lattice. For instance, let us remove some of the vertices of the lattice. Let's say induce a hole in the lattice. How does this?
Should be the same phenomena. Should be the same phenomena. It is also disorder. It's also you introduce some kind of disorder here, and whenever you have disorder in dimension 2, you will see the same phenomena.
So in the original first problem,
yes,
the geodesic problem, somehow the idea, I mean, the dream, which I don't think ever comes true, is that the geodesic theory can tell you about the geometry of the surface or geometry of configuration in space of particles. The question is, can we, like, if all the particles somehow randomly move around, but they avoid the hole, then I would know the hole exists there. Is there such connections?
I would say that we're looking at the large distances and large times, and in this situation, geometry basically became trivial, it disappears, and you see just discrete objects instead of geometry. And these discrete objects, like point fields and stuff like that, they can be described, hopefully. And
another naive question: why is it the same? Is it the case in nature that this random walk is always completely homogeneous? Like, what if movement of? Because here you have this spatial dimension. What if the velocity of the movement of the object to the right is more than the movement of the object to the left?
There is a huge literature. There's a lot of research, and this is what is called random walks in random environment. A lot is known about it. Some open question open. It depends on details, symmetric or asymmetric.
So asymmetry is.
But it's a lot of it is known. It's another subject, but very studied.
Sorry, yeah, maybe it's along the lines of one of the previous questions, but when you mentioned you have a random walk, you have actually, it can be associated and has connection with this axially symmetric process like TASAP with integrability, which usually TASAP models or ASAP models, they usually people relate them with Markovian process and other. But when you go to this CFBM fraction, it sounds to me like you reduce stochasticity a bit, like randomness. And do you think in this CFBM there is still relation to this axially symmetric, or does it change anything?
I don't see why I'm reducing randomness. Actually, there's a lot of randomness.
Yeah, sure.
It
sounded like
it's slightly.
You say you need to do something that it depends on your initial data.
Not the initial data. What you did in the past.
Yeah, in the past. That's what I mean. Like
it's not initial data. You started minus infinity in time.
Right.
And then you do it, right? And then you come to time n, but coming from minus infinity, so there is no initial data. It's kind of self-generated randomness.
Yeah, by initial data, I mean you still do the same thing, what you have done in the past. Is that true? This is what you said, I think. So.
Yeah, I don't know.
So the short point is in this
symmetry, what you also mentioned, I didn't get what the question.
Relation to integrability in this CFBM, is it clear or not?
First of all, I want to say that nobody considered this coalescent fractional Brownian motion mathematically is not yet constructed. It can be constructed, no question about, but it's not. It was a thesis of somebody to construct it Brownian motion. It still needs some work. So mathematically, this object is not yet constructed. And in reality, and I'm not telling it in this talk because it will be too much, that the right object is not just coalescent Brownian motion. That would be enough in the dependent case. But in dependent case, you have to consider what is called web, coalescent fractional Brownian web. And it means that you start not from every point at given time, but from every point at every time. And then you have to construct this object, and this object will give you the fixed point for what I'm discussing. We can talk more about it.
More questions, if any. I must say we are very lucky. This is yet another fantastic talk. Let's thank Konstantin again.
Thank you.